In this example, we want to find the intervals on which f is increasing and decreasing, and we're given f of x equals x to the 2/3 times the quantity x squared minus 4. Okay, well, this process will of course involve the derivative, so let's bring up our steps. Okay, step 1 is compute the derivative. Alright, so it looks like we have a little bit of power rule along with the product rule here. F prime of x is, okay, so remember the product rule is a prime b plus b prime a. So let's see here. A prime is 2/3. X to the 2/3 minus 1 is negative 1/3. So there's a prime b. X squared minus 4 is b. Plus b prime, well, that's just 2x times a times x to the 2/3. Okay, well, there's the derivative. The rest is honestly just algebra, but it's a fair amount of algebra. So let's take a look. I guess we can simplify this a little bit since we have 2x times x to the 2/3. Well, this is x to the 1, so we can just add those exponents. 1 is 3/3. This would give us 2x to the 5/3. So let's write that instead. 2x to the 5/3. Okay, step 2, use the critical points to define regions. So that means we have to find the critical points, which means we have to know what critical points are. Recall that the critical points are where f prime either equals 0 or does not exist. So we're looking at those places for the derivative. So let's go ahead and set this equal to 0 and see if we can solve that out. And we'll pick up any points where it does not exist in the process. Okay, equals 0. Now, it's a good thing we theoretically spent many years learning algebra before getting to calculus, because we'll need it in solving these types of equations for 0. There's a few ways you can go here. You could bring this x to the 1/3 down to the denominator and then work on finding a common denominator. That's not the tack I'm going to take. Instead, I'll use a method that I find very direct that factors out the term with the most negative exponent. We can think of this as a technique. Factor out the term with the most negative exponent. Well, we have two exponents to choose from. We have negative 1/3 and 5/3, so clearly negative 1/3 is the most negative. Sometimes you get one where they're both positive, so just choose the smaller of the two. That's technically the most negative if you picture these things on a number line. We can think of it as the one furthest to the left on the number line is the one that you factor out. I say the most negative. Okay, well, what happens when we factor that out? I'm actually going to bring the 2/3 along with it for the ride. So I'm going to factor out 2/3 x to the negative 1/3. Well, that leaves behind x squared minus 4 plus, okay, 2 divided by 2/3 is 3, right? Just as an aside, 2 divided by 2/3 multiplied by the reciprocal, 2 times 3/2, and that's where our 3 came from. Times, well, we factored out x to the negative 1/3, which means we divided every term left behind by x to the negative 1/3, and when we divide, we subtract exponents. So here we have x to the 5/3 minus a negative 1/3. Now, before you start having serious doubts about this method, look what happens here. And this will almost always happen. You'll get something really nice right here. 5/3 minus a minus 1/3 is 6/3, which is 2. So check this out. We have 2/3 x to the negative 1/3 times the quantity x squared minus 4 plus 3x squared. And that's starting to look a lot better. We can go even further here. 2/3 x to the negative 1/3. Let's make this 4x squared plus 4, make that minus 4. Minus 4. And each one of these is equal 0, by the way. I'm getting a little sloppy here. Equals 0, equals 0. And just to really simplify things, let's factor a 4 out of these second two terms here. So that gives us, how about 8/3 x to the negative 1/3 times the quantity x squared minus 1. Okay, equals 0. Okay, we're really looking for two things here. We want to know where the function does not exist, and that's where this bit equals 0, x to the negative 1/3. So the derivative does not exist when that equals 0, since this negative 1/3 actually brings this x down to the denominator. So it does not exist at x equals 0. So that's one of our critical points. And let's see here. We have x squared minus 1. This is where the derivative equals 0. So just to distinguish that, I'll be very clear. F prime equals 0. This is where f prime does not exist. Okay, so we need to set that equal to 0. Well, let's be very direct with it here and take it all the way down to x plus 1, x minus 1 equals 0, which gives us x equals 1 and minus 1. Okay, so we have three critical points. X equals 0 and x equal plus or minus 1. Plus or minus 1. And you may be asking, why do we have to check regions where the derivative does not exist? That seems like a strange thing to do. Well, let's just imagine some functions real quick. How about this function? Right there, the derivative does not exist at that corner, but it clearly goes from increasing to decreasing. So we'd want to check the points where the derivative does not exist, right, for some point C here. Or maybe we have something like this. Imagine this function. Let's do a vertical asymptote. How about this? Comes up. Okay, the derivative does not exist at that point C where the asymptote is, but note that it goes from increasing to decreasing across the asymptote. So we would want to check the regions defined by that asymptote where the derivative does not exist. So then you may be saying, well, does it always change from increasing to decreasing, or vice versa, when we go across an asymptote? No, not necessarily. Consider something as simple as, say, 1 over x. Okay, and these are very rough sketches, but note that it's decreasing, and then we hop over our asymptote at x equals 0 here, and it's still decreasing. So just because we have an asymptote doesn't mean it switches between increasing and decreasing. Okay, so that's just a lot of rapid-fire calculus real quick there. But let's go back to focusing on our function. Back to our steps, we have step 2, use the critical points to define regions, and then in step 3, we'll check each region to determine whether the derivative is positive or negative. Okay, we can do that. So let's make a sign chart here. Okay, so this thing here is our derivative. Okay, that 8/3, etc. So let's set up a sign chart and check those regions. Okay, so there's our number line, essentially. And then our critical points, and thus our regions, are 0. So we'll do 1, 0. And then we have something over here at 1, something over here at -1. So let's test all these regions. So we need test points. So how about x equals -2 over here in the left region? X equals, how about -1/2 between -1 and 0. Similarly, x equals 1/2 between 0 and 1. And how about x equals 2 from 1 to infinity? Though again, you could choose any point in these regions as long as you're not choosing the boundary point. You'd get the same results. Okay, and then we want our chart to test points here. So I'll say x and then f prime of x, which is what we're testing. Remember, we're testing in the derivative, not the original function here for increasing and decreasing. So 8/3 x to the -1/3 x plus 1 x minus 1. Now I'm writing it in its most broken up form possible because I'm just interested in where the function is positive or negative. Now if you're doing this slightly different, it's no problem, right? You may want to keep it a little more condensed and just plug in once and get your plus or minus that way. I like to break it up and test. That way I can very clearly see what's happening in each little chunk of this function. But as long as you're testing your points and getting pluses and minuses, you're doing fine. Okay, so just to be clear, this bit here will be our derivative in this process, f prime of x. Okay, and then what do we plug in? Well, we have all our test points. So we have -2 for x, -1/2, +1/2, and +2. Okay, we don't need to know what the derivative is at this point. We just need to know if it's positive or negative. So plugging in gives, well, x to the -1/3. We plug in -2, that's negative. -2 plus 1 is negative, and -2 minus 1 is negative. Negative times negative times negative is negative. Okay, so this whole region up here gets a big fat negative where x equals -2 lives. Moving on to x equals negative 1/2. Plugging in, well, negative 1/2 to the negative 1/3 is negative. Negative 1/2 plus 1 is positive. Negative 1/2 minus 1 is negative. Negative times negative is positive. There we go. Moving on to 1/2. Plugging it into x to the negative 1/3, positive. Remember, the negative 1/3 just brings this down to the denominator. So that's what's going on there. Okay, so 1/2 plus 1 is positive. But 1/2 minus 1 is still negative. So we have positive times negative, which is negative in this case. And finally, plugging in 2, positive, positive, positive. Positive times positive is indeed positive. Now, don't get the wrong impression that these always alternate from region to region. They don't. So that's a dangerous habit to get into, just assuming that they always alternate. Sometimes you'll have negative, negative, positive, positive, right? So you really have to test each region to make sure you know exactly what's going on. Okay, well, let's finish this out. Remember, the original problem asked us to identify where the function is increasing or decreasing. We can now do that. It's increasing where the derivative is positive and decreasing where the derivative is negative. Oh, and let's finish filling out our number line up here. This was positive in this region, negative, and positive. All right, the number line is not completely important, but I like it because it gives a nice visual representation of what's happening, and it makes it much easier to grab our intervals from there. So then we can see that it's increasing anytime we have a positive there on our number line. So how about -1 to 0? Soft brackets, of course. Union with 1 to infinity. We use soft brackets because the function is neither increasing nor decreasing where the derivative equals 0. And that's what happens at the endpoints. Okay, and then decreasing wherever it's negative. So how about -infinity to -1, union 0 to 1. And there you have it. Now, a fun thing to do at this point might be to graph this whole function, the original function, in Desmos, just to verify that it is indeed increasing and decreasing in those regions that we expect. I won't do it here, but certainly it might be interesting to try on your own.